Starting from number 7 again, I could put the y here, but then we're going to pull the switch anyway, so I'm going to put x instead equals 3 over, and then y minus 2 and plus 1. Minus 1. And so then from there, I'd probably get rid of that minus 1 actually. And so if we were there, I'd go plus 1 to get rid of the 1 on that side. Now we have x plus 1 on the left equals 3 over y minus 2. And then it's weird to get y by itself if it's on the bottom of a fraction like that. So I'd probably times that to both sides or something, and we'll end up getting rid of the fraction that way, because I just don't like having a fraction. So we'll put a y minus 2 times into both sides, and the y minus 2's will cancel on the right-hand side. So then on the left-hand side, we got y minus 2 times x plus 1, all equaling 3, without anything else on the right-hand side, and it's good. And now we'll try and get the y by itself. And it looks real bad for a second, like we're going to have to FOIL it. But since that factor is x plus 1, doesn't have a y in it, we'll just get rid of that whole x plus 1 thing. That way, we almost have y by itself anyway. It'll be just the y minus 2 with the x plus 1 gone, and then equals 3 over the x plus 1. That'll be good, because now we can just plus the 2 on both sides, and now we got y by itself. Here, let's clean that up. Y by itself equals just 3 over x plus 1 plus 2, all of it. And that's your inverse function. Looking good. Okay, next deal. Rewrite each equation in exponential form. Okay, so if I saw this one in exponent form, that's a log base 15, so we're talking 15 to the this power, so 15 to the minus 2 equals 1 over 225. That's what we're talking about, putting in exponent form. And then on number 9, same idea. We have a 7 to the v power equals u. That's all we're looking for. Let's see here. Let's put this junk now on numbers 10 and 11. We're hoping to put things into logarithmic form. So that'll be a log there, however you write that, whatever, log base 7 of 49 equals 2. Just pulling the switch. It's this number to the that equals the other, or some kind of thing. And then number 11, similar. This is log base number 9 of v, pretend that says v, equals u. Looking good. Then number 12, we're just evaluating each expression. So then log base 6 of 216. If you're comfortable with figuring these in your head, then go for it. Otherwise, remember what this is saying is, I'm saying 6 to some power I got to figure out equals 216. That's what we're saying. 6 to some power equals 216. That's what it means to evaluate a logarithm. 6 is the base number to some power gives you 216. We just got to figure out the power. How many 6's does it take? And that's just a matter of guessing. We have 6 times 6 is 36. Times another one is 216. Looks like it took 3 of them. So then all we end up saying is just, I guess it's just 3. And that's the power we'll need. So that power we would need is a 3. So then when we evaluate the logarithm, that's all it means. Is this whole thing just equals 3. Same idea. This one's just weirder on number 13. We have 5 to some power, question mark power, equals 1. And he's got to remember, 5 to what power makes 1? That happens to be 0. 5 to the 0 equals 1. For reasons we could always go over again. Anyway, so that's just 0 in this case. Now solving each equation here, we got to we got to solve these equations. Maybe looking like by the old, what is it called, like basis formula or something. Like basis property, we'll call it, yeah. And so if I had this 3 to the n plus 1, if I saw that, I would also remember that 27 is also a power of 3. That's 3 to the 3. And if that's the case, then that means n plus 1 is the same thing as 3. So we can just not worry about the base numbers anymore. So n plus 1 equals 3, or in other words, keep the exponents, This n plus 1 equals this power of 3. And then we'll just solve for n from there. So then n equals just 2, I guess. Looking good. Number 15, if we add this one, 64 is a power of 8 as well, so that'll be good. So we can say 8 to the m minus 3 equals 8 to the 2. And then you could just say don't need the 8's, m minus 3 equals 2, and then solve that one from there. That'll be good too. And then tougher one that I see would be this following one. Same ideas though. We have 81 and 27 and 243 all involved. They all seem to be powers of 3, it seems, and so I think 243 is 3 to the 5. And so if that's the case, let's see if we can make this work. 81 is the same thing as 3 to the 4th, but it has that 2x on top of it, so we'll remember that. This is all still to the 2x power. Timesing with 27, that's to 3 to the 3, equals 243, that is 3 to the 5. So if that's the case, let me get these arrows out of there. I thought they would help, but they're too messy. If that's the case, then we'll say, well, we're almost there. These are all powers of 3 now. It's a little weird having the stacked exponents, so maybe we'll clean that up. 4 times 2x makes like 8x. So we'll say this is 3 to the 8x times 3 to the 3 equals 3 to the 5. And then the only thing to remember before we finish this up, here, erase, is that times is like plus in exponent land, just like in logarithm land. So then this is 3 to the, and then these things that are timesing, I can plus them. This is 3 to the 8x plus 3 power equals 3 to the 5. This is not the only way to approach this. I used to do it a whole different way. Anyway, then we don't need the 3's, and then we can just say 8x plus 3 equals 5, and then solve that thing out until we know what x is. That's what I would do. Okay, expand each logarithm. So to expand each logarithm, we're going to write it as a number of logarithms. We have, this would be, divide is like minus, remember. So this is log x minus log y, both common logs, and that's all they're looking for there. Log x minus log y, because divide is like minus here. And then number 18, we have log base 2 of all this stuff. If I have a 5 power on the outside, different people will handle this differently. What I might recommend just because of the way we've been doing things, is we would say log base 2 of, and then I would distribute the 5 in there. It's not really distributing, but it's like that. And so then we'll say u to the 2 to the 5, that's u to the 2 times 5 is u10. Pretend that says 10. And then v to the, it's just v to the 1 to the 5 in there, so v to the 5. I'll put that 5 to everybody, so that's u10 and v5. Then we can expand this to multiple logarithms. I'll go downstairs for a second. This will be log base 2 of u10, and then log base 2 of v5. And just remember, these things were timesing before. So now they're plussing, times is like plus when you expand. And then we're just going to take the powers on the outside. So this is a 10, u to the 10th on the inside. So remember, that's 10 times of log u plus, and then this exponent comes to the outside as well. So that's 5 times of log base 2 of v. Oh, those are both base 2, huh? It's supposed to be base 2 on everything. Pretend like I wrote that. Anyway, so we got 10 log base 2 of u plus 5 log base 2 of v is what I'm looking at. Then thereafter, the next couple, we're supposed to be doing the same process but backward. We're supposed to take multiple logarithms in a single expression and turn them into a single logarithm. And so, look at us. If we had log base 4 of a all divided by 3, that is basically all a single logarithm. I think all they're saying is, can we deal with that divide by 3? So remember this. Divide by 3 is the same thing as 1/3 timesing with the logarithm. So this is 1/3 times log base 4 of a, which is no big deal. But also, if I want to make it all become part of the logarithm, I'm going to put that 1/3 inside as an exponent. So this is log base 4 of a to the 1/3 power. Or you might remember a to the 1/3 power is log base 4 of the cube root or the 3 root of a, just so you know. That might also come up because a third root or a third power is the same thing as a 3 root. Okay, and then number 20. Let's see. Number 20, if I were to make this into a single logarithm, probably the 6 and the 18 got to shoot up to exponent status, and so we'll start by doing that. The 6 will go, we got log base 9 of u to the 6th power minus log base 9 of v to the 18th power. Both of them all powered up, and then just remember that minus is like divide again when you put them all into a single logarithm. So we'll say this is log base 9 of, and then minus will be like divide. So we say u6 divided by v18. Looking good. That's all we got to do. It's all a single logarithm now. Okay, solving some more equations here. These ones look like we'll have to go more logarithm on them, so let's just see if we can get x by itself best we can by getting things into logarithmic form. On this first one here, I'd probably get the 5 out of there. Here, let's rewrite that down there. 5 times 13 to the x minus 9 power equals 3.1. If I were doing this, I'd probably get the 5 out of there. So I can just make it, it'll be a little more simple to deal with the logarithm at this point. Because now it's just 13 to some power, x minus 9 power equals whatever. 3.1 divided by 5, I believe, is 0.62, so I'm going to put that. Because you could just divide those numbers. I believe it's that. And so then, from there, guys, now this we can put into logarithm form. Now that we got the old 13 to some power, now we can go logarithm on it, and that'll be a log base 13 of 0.62 equals x minus 9, and now the x will be easy to get by itself. So I'm going to go ahead and plus 9 to both sides. Then the x is by itself. Now we just got x on the right hand side equals all of that. It's log base 13 of 0.62, all that mess plus 9. And then again, remember, if your calculators won't let you put in stuff like that, you can, if they won't let you choose your base number, you can always do, by change of base formula, that's common log of 0.62. Don't forget your little point on the 62, over common log of 13, and then all of that plus 9. You can get that as well, either or. Looking good. Okay. Probably I won't give you as much advice on the other ones. And then just remember, you can run that through a calculator and then it shoves that decimal at you for an answer. On this next couple, I won't give you all of it, but we'll give you enough to at least get going. And so then, let's see here. If I saw number 22, I'd probably get rid of the plus 2 with a minus 2. Then we'd have 2 to some power. Be like the 3 minus a power equals like 15 at that point. And then we'll just go into log form one again. It'll be log base 2 of 15 equals 3 take away a. Just be careful in solving this one because, again, you'll have to minus the 3. Oh, it's log base 2. Minus the 3, and then you'll have a negative a still sitting there. So don't forget. Here we go. Showing you the whole thing. Then just don't forget now we have log base 2 of 15. I'll take away 3, but it equals negative a. So once you're all done with that, you might want to divide by a negative or something like that to get the or the a by itself. Divide by a negative 1, then it's just the same thing as what you had, but it's all of that times by a negative. So a negative number, or a negative 1 timesing with log base 2 of 15, all plus 3, and then times that answer by a negative. Boom. Once you get an answer. And you can do change of base stuff with that too, and all that. Cool. Bloom, 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 bloom. Then let's see, on number 23, similar idea, I'll get rid of the 8 with a minus 8, and then I would also probably get rid of the 7, because now we'd have negative 7 times 16 to whatever power equals, what is that, negative 55? Negative 55. And so then probably I would get the 7 out of there as well. Dividing that, now we have 16 to the m plus 10 power equals a negative into a negative is positive, but then whatever 55 divided by 7 is, that's nasty, so I'll leave it as a fraction. Then we'll put it into log form, b log 16 of 55 sevenths equals m plus 10, and then you finish it like we have been doing the others. Dot, dot, dot. Keep on going.